SwayamPrabha. Digital India. Educated India.
Welcome to this Gyan course on phase field modeling of fracture, fatigue and chemo-mechanical degradation of materials. And we have with us today, of course, Professor Emilio Martinez Paneda. I'll give you a brief introduction about him. He's an associate professor at University of Oxford. So prior to Oxford, he was a reader at Imperial College, where he led an interdisciplinary research group from 2019 to 2023. Before that, he was an 1851 research fellow at the University of Cambridge. His recent research focus has been on addressing fundamental scientific challenges that can accelerate our transition to net zero carbon society and assist in tackling our energy and climate crisis. Professor Paneda has been the PI for over 7 million British pounds of funding in the past 5 years, including ERC Starting Grant, UKRI Future Leaders Fellowship, and his work has been recognized through multiple awards, including the 2021 UK Young Engineer of the Year by the Royal Academy of Engineering, the 2022 Imperial College President's Medal for Excellence in Research, and the 2024 ICAM Award and John Argyris Award, right? So with that, we have an absolute pleasure and honor to have him here for the whole week, and I hope that you really get benefited from his stay here, okay? So Emilio, the floor is yours.
Thank you, thank you. Thank you. Thank you all, I hope you can hear me well. Thank you, Anna, for this very kind introduction and inviting me to this course. It's really a pleasure for me to be here, and I look forward to meeting all of you more in person and to interacting with you over this week. I hope you also learn a bit this week. So I understand that I've seen your profiles, what you're interested in. I understand that I'm dealing with an audience that spans different types of backgrounds. So I'm going to try to make sure that I cover something that is of interest to all of you, and at the same time that you can all follow, no matter what your background is, what I'm going to go through. Which means that I'll start with something that is probably basic to many of you. I know a number of you have a background in fracture mechanics and fatigue, but not all of you, so I think it's important that we cover some of the aspects. So it will be a bit of a recap, maybe the first lecture, Monday morning, but I think you'll also find it interesting. Everyone will find it interesting, I hope. And also, I think it covers or highlights, it's basically a summary of some of the key concepts of fracture and fatigue that you need to understand then later on these phase field technologies that have been a game changer in all of these fracture and fatigue problems. So before I get into the business, I'll overview a little bit of what we're going to see this week, and I'll tell you a little bit more about myself. So as you heard, my name is Emilio Martinez Paneda. I'm an associate professor at the University of Oxford, where I lead the Mechanics of Materials Lab. You can find our website here. We upload all the codes that we develop to our website, and we use a variety of finite element platforms like COMSOL, Phoenix, Abacus, our own MATLAB and C++ codes. So I'll be discussing some of those, and you're welcome to download them and try them. I understand that I wanted to do a bit more hands-on type of week where you will do some examples yourselves, but it's a bit complicated because of the different licenses, different platforms. I know some of you work with one package, some of you work with another package. So the way it's going to work is that I'm going to tell you the main three approaches that we use, which is COMSOL, Abacus, and Phoenix. I'll explain what are the ingredients, how to use them. But then I'll let you freely download the codes and use them, and then you come to me with any questions that you may have. So all the codes are here. There's somewhere written codes, and you can download them there. But yeah, before I start my lectures, just a few words about myself. So as you can probably figure out from my accent and from my name, I'm not British. Well, I am a dual British-Spanish national now, but I was born and raised in Spain, in the north of Spain, in this area here. This region in red here is called Asturias, and it's a very beautiful region. Of course, I'm very biased, but I hope you have the chance to visit at some point in your lives. It's a very nice region. As you can see here, we have nice beaches, cathedrals, mountains, cows, so it's quite a nice place. But it's been a long time since I don't live there. I did study my undergrad there. I did general engineering, with some sort of a specialization in civil and mechanical engineering. This is very common in Spain. We study in our home university. I think different to India, we don't have prestigious institutes like IITs, more or less are all the same. So we studied in our home university. It's cheaper. And then my PhD or my academic career took me all over the place. So my PhD was mostly done in Denmark, so somewhere here. And then I spent some time also in the University of Luxembourg and University of California, Santa Barbara, and mostly also in the University of Cambridge with Norman Fleck. And then after my PhD, I continued as a research fellow in the University of Cambridge, and then I began my academic career at Imperial. This was September 2019. I stayed 4 years at Imperial, where I was a lecturer, which is equivalent to US assistant professor. Then became senior lecturer 2 years later, and then a year later became a reader. And then since a year and a half ago, I moved to the University of Oxford. It's a great place. I feel very privileged to work there. It's a very old university with old buildings, as you can see here, and very old traditions. We're a bit Harry Potter type of style, so we have these formal dinners. Some colleges have it we all belong to a college. It's a bit of a long story. And we have this kind of formal dinners with our gowns and so on. Some colleges have it every day of the week. My college has a couple of days per week. So if you're around in Oxford, let me know. I'll be happy to invite you to one of those dinners. But yeah, it's a great place. I think it's a very international environment, of course. There's people from everywhere, also from India. Lots of people from India, in fact. But it's, the best students from all over the world, so it's really a pleasure to work with people there. It's really a great place. I feel very privileged to work there. And what I do at Oxford is I lead a research group called the Mechanics of Materials Lab. And it's a very diverse and relatively large research group. It's one of the largest in the department, I've been told. So we have now 11 postdocs and 10 PhD students. And you can see it's a quite diverse group. This is a picture of my group in this past summer, enjoying a pint of beer in a pub in Oxford. You can see there's some people from India. You can see here Tushar. Tushar is now an academic at IIT Bombay. This was just before he left. Ratul here. Ratul did his undergrad in one of the IITs, but I don't remember which one. Then he did his master's at University of British Columbia, then PhD in Cambridge with Norman Fleck. My past advisor is now a postdoc in the group. But anyway, we have people from all over the place. You can see this is someone from the Czech Republic, China, Spain, of course, Serbia, the Netherlands, Brazil. People from all over the place. So a very international group and all quite friendly, I think. And these people are, by the way, the ones who deserve the credit for all the work that I'm about to show. And of course, all these people, what they do is they solve challenges that sit at the interface between mechanics and other disciplines, such as material science, a lot of it, of course, chemistry, but also geophysics, biology, and others, civil engineering, construction, and others. So you can see here some of the examples in our logo. So this is our website, by the way. You can see this codes tab. Here you'll find all the codes that I was mentioning before. You can download them and try them. But yeah, basically what we do is work mostly on problems that are related to the climate and energy crisis. So a lot of the funding in the UK is very challenge-driven. So the UK government kind of tells academics where to work. And of course, the UK government, like many others, is worried about the energy transition, about pollution, about CO2 emissions, climate change. So there's a lot of interest in tackling mechanics and materials problems who are basically at the bottleneck. So we're really important when it comes to tackling this energy transition. So yeah, there's a lot of funding in that direction, and we have embraced that with relish. I mean, the problems are exciting. They're fundamentally challenging, but at the same time, useful to society, interesting from an engineering perspective. So we're working on a wide range of problems along those lines. So some of them, you can find them here. So we do a lot of work on structural integrity, related, of course, with the energy transition, but not only, of course, lots of interest problems across. If we think of the application, offshore wind energy, nuclear power plants, and so on. We're also interested in iceberg calving. So this is, again, related to climate change in the sense that basically whether, I'll talk about that more later, but whether the sea level will rise a certain amount or a bigger or smaller amount depends on these fracture problems, which is basically these crevasses growing in an ice sheet. So we're trying to use fracture mechanics to predict, sea level rise more appropriately. Rock fracture as well, of course. The mining industry consumes 6% of the world's energy consumption just by breaking big rocks into smaller rocks. So by understanding fracture mechanics, we can bring down that number. Low carbon cements, there's a lot of interest in cementitious materials, and particularly in developing, changing the Portland by other binders, the Portland cement by other binders. So we need to understand, do some sort of micromechanics to understand how these new low carbon cements will behave, what will be their structural performance. Corrosion and corrosion fatigue, so problems at the interface between mechanics, material science, and chemistry. These are critical to many applications. I mean, they've been a problem for society for a century, and they're critical to many applications like nuclear power or offshore wind energy. Concrete durability as well. There's a lot of work going on corrosion of concrete. A lot of computational mechanics. In fact, we do both experiments and modeling in my group. I would say 30% of the group does experiments, 70% does modeling, roughly, those numbers. But mostly this week I'll be focusing on our computational efforts. So we do a lot of work also in developing new methods, new computational methods, new computational techniques. We also work in composite materials, fiber-reinforced composites, but also smart materials, also lithium-ion batteries, and also, of course, hydrogen embrittlement. This is one of the core areas for our interest. There's a lot of interest in hydrogen material interactions, and I think our group has really embraced that. I would say probably 40% of the group, if not more, are working on hydrogen embrittlement. So yeah, this is basically an overview. There's other problems, and some of which I will be mentioning today, but as you can see, mechanics is kind of the link. The societal motivation is more, energy and climate crisis, but it's mostly mechanics what drives all together. And yeah, exciting problems that sit on the interface between other problems. I think in general, it's good to say that most interesting or unsolved scientific problems sit at the interface between disciplines. We know relatively well how structures and materials behave on their own, but the moment you bring an aggressive environment into the picture, that changes completely the picture. So this is what we are interested in, fundamental problems that can have also an impact on engineering practice. I should say, by the way, that the way I thought of running this course is that you can interrupt me at any time. You can just raise your hand if you have any questions. I will probably do a break so there's a break well, I'll show you the table of content. Let me go to the structure of the course. So you will see the structure. You may have received this, I don't know, but anyway, I think you'll get the slides, so you'll see it on the slides. But you see the structure here. You can see that we have basically lectures of 1 hour and a half, followed by a half-an-hour coffee break. And of course, I look forward to meeting some of you over the coffee break if you want to approach and say hi and tell me what you do. And then we have another 1 hour and a half. I don't know if it's too much to go an hour and a half straight. I think they say humans can only concentrate 100% by 45 minutes. So maybe I'll do 45 minutes. I'll stop to see if anyone has some questions for 5 minutes and then go back into business. As you will see, we'll start today with an introduction to fracture mechanics. Again, I will cover some things that some of you or most of you have probably seen already, but I think it's good to have it reinforced in your brain. And fracture mechanics is not taught in the same way and everywhere, so maybe there's also some new ideas in there. Then I will discuss facial fracture for an hour and a half. Tomorrow we'll get into implementation and practicalities. I'll show you how you actually work with facial fracture in finite elements. I'll discuss some techniques and tricks on how to improve convergence and things like this. I'll discuss applications, showcase some applications in the second lecture tomorrow. And then I have a seminar here, well, not here, I don't know, it's some other room, KCB 222, that is focused mostly on the hydrogen embrittlement problem. So I don't know if attendance to the seminar is mandatory, but I strongly encourage, because basically the day afterwards I'm going to talk about hydrogen, but I'm not going to repeat the same thing of the seminar because that would be a bit of a waste of your time. So I'm going to say things that require knowing what I said at the seminar. So I think it's important, unless you want to be completely lost for 3 hours, I think it's important that you come to the seminar tomorrow afternoon. Yeah, then on Wednesday, I will start with facial fatigue, extension of these facial malleoles to fatigue, which is a very, I would say, very much ongoing research topic that is very active and growing quite fast. Then I'll say more things about hydrogen, so I will build on what I explained over the seminar, and I'll go a bit more deep. I know this is a topic of interest to several of you, so I'll spend a bit more time on hydrogen embrittlement. And then I'll go into multiphysics phasing modeling, tell you a little bit of, if you have any sort of multiphysics problem, it could be the corrosion of concrete, it could be batteries, how do you incorporate that, how do you join this with phase field, and how you actually do it, in COMSOL, Abacus, any other tool that you have. And then the last day I will discuss phase field modeling of corrosion for an hour and a half, and then battery degradation for another hour and a half. So yeah, you stop me anytime. I will do a stop, maybe not today because we start a bit late at 45 past, but at some point I will stop and you can ask me any questions. And of course, just because before the coffee break, you'll get the chance to ask questions. Okay, so we start with fracture mechanics. So this is something that many of you have already heard before. As you know, structures fail and all the time. You can see some examples here. And we need a discipline, we need a technique to be able to understand what's happening here. So, okay, what can we do? How was the discipline developed? And I think the best way to look at fracture mechanics is by taking a historical perspective. Okay, when did humans realize that things were falling down and they needed to come up with a scientific discipline that would explain how things fall down and what to do under those circumstances? And I think the topic is of course old. Things fail for have been failing for quite a long time. Of course, many old constructions remain. You would still, if you go to Rome, you will find the Colosseum, which is an amazing structure. But of course, for every old structure that is standing, many of the temples that we have around us, there's many others that have collapsed, and we just don't know about it. For example, just 5 kilometers away from the Colosseum, you have this Fidene amphitheater that collapsed, and 20,000 people died. So a lot of, we know about the Colosseum, we don't know about this, so many things fail. So I think historically it's fair to say that engineers back then, what they did was more of a trial and error. They try things, when they didn't work. So I think this amphitheater was actually made of wood. They said, okay, wood doesn't seem to be good for these things, we'll do something else. So it was very much based on experience. In fact, I think the legend goes that the Romans will ask the engineers and their families to sleep below the bridge they had just built, or the aqueduct, over the first night, just in case it fell down. They will be the first to suffer the consequences. I'm not sure if that's true, but it's I guess a way of natural selection. I think what it was in favor of the old engineers is that back then they were mostly working with brittle materials such as rock, mortar, or clay, and that's good and bad at the same time. Of course, they're brittle, but at the same time they work very well under compression. So under tension, no way, but under compression they work very well. So of course they soon learned that what they had to do is to work under compressive loads, so they came up with arcs and other ways, so that make sure that they didn't have any tensile loads. And I mean, they were very limited on what they could do. You can say always the same shapes, but at the same time they didn't experience those tensile stresses that will fail their material. Then the Industrial Revolution came, and then new materials came around, metals being particularly prominent, and those, of course, together with advanced design methods, allows us to design very complex structures, so not only dealing with traction loads, but very complicated stress states. So that was, of course, a revolution, but it also brought new challenges and, of course, new fracture mechanics problems. And in general, you could say that, failures fail due to one of two reasons. One is human errors, so some errors in the design, construction, or maintenance phases. This is things that we could have prevented, so things failed under conditions that we understood, but we made a mistake, and as a result we got a failure. Or things fail due to the use of new materials or designs. So this is unexpected and unknown behavior. So failures in modern aerospace technology wouldn't, of course, happen if we didn't have modern aerospace technology. So every time we use a new material, every time we use a new technology, there's a challenge that comes to it, which is related to our lack of understanding, basically. So if we think of failures due to new materials and designs, we could think of the failures in polyethylene gas pipelines that occur in the UK and many other countries in the 90s. So we used to use metals for transporting gas, and we still do. But there was an idea to replace them by this polyethylene. We thought, okay, it's lighter, it's cheaper, it doesn't suffer from corrosion. But then what they didn't realize is that it suffers from other problems, such as some sort of creep damage, which takes a long time to happen. So it's not something that you see quickly in the lab. So when they did their quick experiments, they didn't see it. But then over long time exposure, you saw those cracks happening, a lot of explosions, a lot of issues there. Another very classic example is the Space Shuttle Challenger disaster. So this happened a long time ago. I suspect none of you were born back then. I wasn't born back then. But if you ask your parents, mine claimed that it was a big deal. It was all the people died, all the astronauts inside died. It was a big problem for the aerospace industry. And of course, this was NASA, so they were testing things properly. They knew what they were doing. But the problem is that one of the gaskets that they were using was tested under room temperature conditions, and it became much more brittle under low temperature conditions. And this gasket was exposed briefly to low temperatures, but for a sufficiently long amount of time that it caused embrittlement and the fracture, and then this disaster. So every time even though we test things carefully, every time we deal with new technologies, we need to think very carefully about what we do. Other classic examples are the Liberty ships. This is what you probably heard about, because it's the classic example that gives you the birth of fracture mechanics. So as part of the Second World War, the US was trying to help Europe, the Allies, so they tried to build ships as fast as they could. So they built, I think it was 3 ships every 2 days through the use of technologies that will really accelerate ship production. So in this case, they use, back then ships were mostly riveted, so they had riveted joints. But the US decided to accelerate the ships, they decided to use welded joints. And nowadays we weld, most ships are welded, but back in the day it was a new technology. And what they didn't realize is that those welds will suffer, particularly in the low temperatures, So lots of failures happen. I think they saw cracking, I think they did almost 3,000 of the ships, and they saw cracking in 1,600 of them. So more than half of those ships underwent cracking, and 18 of them cracked in half, as you see here, with, of course, a big loss of lives and all of our resources. And this happened, of course, due to a lack of understanding of how those wells will behave, and some sort of brittle to ductile transition, and some hydrogen embitterment too, when those ships were going through near the North Pole. Another classic example is the Havilland Commute aviation accident. So you may wonder when you fly on a plane why the windows are rounded. Well, of course, you know that sharp corners will lead to stress concentrators, so that's why we make our windows rounded. And you will see that back in the day, in fact, the windows were rounded, had sharp corners like they had in our house, basically. And you can see that nowadays it's quite blunt, quite smooth. And you can see why. I mean, this is a finite element analysis. You can see, of course, that in sharp corners you're going to get a higher stress concentrator, so you're going to have higher stresses. While if you have smooth windows, then it's going to be a completely different picture. And there were a few accidents, particularly this Havilland Comet aviation accident, where you have fatigue cracks propagating and you lose part of the infrastructure of the plane, and they decided to change into smooth windows. But we're learning from those things, of course, particularly the birth and growth of this discipline of fracture mechanics. Bringing fracture mechanics into standards led to a significant reduction of those accidents. Here are some old data from pressure vessel explosions in the UK. You can see how both the number of explosions per year and the number of people killed or injured are going down dramatically. As we get a better understanding as engineers, incorporate safer practices. And of course, cracks are responsible for most of these explosions, mostly due to fatigue or corrosion fatigue. So how did we learn? Of course, we always learn the same way, using what we call the scientific method. We come up with a hypothesis. We say, things fail because of X. Then we think of an experiment. We do an experiment to test this X phenomena. And then we figure out whether our hypothesis is correct, or we refine our hypothesis and we keep doing experiments. And I guess if you could think of the first person to start doing experiments to try to apply the scientific method to understand why things fail was Leonardo da Vinci. He did experiments on iron wires, and he realized that the strength of those wires was sensitive to their length. So he thought maybe defects play a role, because what is the difference between a large wire and a small wire? The only thing is that maybe statistically the large wire may contain more defects. And this is something that you see, for example, if you do tests on iron whiskers, if you plot the strength versus the size, you can see that there's a very strong sensitivity of the strength of the material to the size. Eventually, if our iron whisker, if our piece of iron is big enough, then we get to some sort of plateau where we have enough distribution of defects, so we're basically in the same spot. So that's what we normally call the strength of our materials. But you can see that if you start going into small scales, look that we're looking into microns here, your strength appears to be very sensitive to the defect size. Up to the point that you can see, the strength is 10 times roughly as large when we have very, very thin whiskers. So when people talk about, graphene being the stronger material in the world, one has to take that claim with a pinch of salt, because graphene is one atom layer thick. So they say graphene is 200 times stronger than steel, for example. Well, that compares a large bench of steel with a one atom layer of graphene. If you consider one atom layer of iron, then the strength of graphene and iron are more or less on the same order of magnitude. So that's the idea. So defects seem to matter. And in fact, nowadays we can predict, either using atomistics or even theoretical considerations, what is the theoretical strength of materials. And we roughly know that it's roughly, the Young's modulus divided by 10. So for silica glass, which is a model material, and we'll discuss it later on, we have a Young's modulus of 70 gigapascals, so a failure strength of 7 gigapascals. But however, when we do experiments in the lab, we show that this failure stress, this strength of silica glass, varies between 1 and 100 megapascals. So lots of scatter, and also much lower than what we expect from theoretical considerations. And this is because of the role of defects. Different samples that look identical in our eyes, actually have defects that are different, that we don't see with our eyes, but are inside macroscopic defects that are different sizes, and those defects will govern the strength of my material. So I'm testing samples that I think are the same, but in reality they're very different. That brings the scatter. And I'm testing samples that, to the naked eye look like a smooth and defect-free, but in reality they have microscopic defects, and that brings a change in theoretical strength, relative to the theoretical strength. So defects are important. This is what they realize. They realized that the failure of components, the failure of structures, the failure of materials must be dependent on small defects growing and at some point due to some combination of stresses or whatever that was. So this is what scientists and engineers turned their eyes on, and Inglis, who was a British civil engineer and mathematician based at Cambridge, he decided to mathematically analyze the stress fields ahead of a defect. He considered an ellipsoid, an ellipse, as you can see here, with in an infinite plate. He was doing things with pen and paper, so he couldn't deal with finite dimensions. He had to approximate things. It was all analytical. So he says, for an infinite, a remote applied stress of sigma infinite, then I'm going to predict what will be my stresses at the tip of this ellipse. And he figured out that this was the solution, and this solution was mathematically rigorous but puzzling to many scientists and engineers back then, because they said, well, we learned a few things here. First of all, if you have a perfect circle, A equals B, then what you see is that the stresses ahead of in the tip of your circle are going to be 3 times the applied stress, and this is something that mechanical engineers know by heart. 3 times you always get the stress that is 3 times as large. And then the other thing you realize is that actually if my ellipse is quite sharp, if B goes towards 0, my stresses at the tip of my ellipse are going to be infinite. So that was puzzling to a lot of people because, of course, there's nothing completely sharp, atomistically sharp. But some defects, particularly in brittle materials, such as glass, as we discussed before, can be very, very sharp, up to the point B could be tiny, nanometers long. And if this is nanometers long, this means that a tiny applied stress will lead to a very, very, very large crack tip stress. So this was a problem. If the stresses are infinite near my crack, then if I apply a tiny load, if I assume that things are going to fail due to the stress reaching a critical quantity, if I apply a tiny load, everything will fail. Because no matter if I have a defect, and defects we just learned are always there, they might be larger or smaller, but they're always there, that defect is going to grow, because if the growth criteria depends on the stress reaching a critical value, then a tiny applied load will reach that value just because the defect is sharp. So that was puzzling. And of course, there's a lot of ifs here. One is that he assumed linear elasticity. Of course, if you assume plasticity, then your stresses will reach the yield stress, and then you get a distribution of stress, and you don't get these infinite stresses. But a lot of materials are linear elastic. Glass is linear elastic, so there will be some sort of non-linear stresses, but it's still reduced to quite a small area. So this result was quite puzzling to many people. How could it be that a tiny applied load will lead to a infinite stress, and therefore things will fail at a tiny load, right? And things don't fail at a tiny load. And then came Alan Arnold Griffith, which was he was a mechanical engineer working for Rolls-Royce at the time, a British mechanical engineer. And he realized that the analysis of of English was fine. It was all mathematically rigorous, but the problem lied on the criteria for growth. It cannot just be that a crack will grow, a defect will grow whenever your stress was big enough to reach a critical quantity. He thought we need to think on this problem based on atomistics and thermodynamics. So he basically conducted some experiments in glass, and he adopted an atomistic perspective where he said, okay, if I look at 2 atoms, then I know that I can plug the force versus the separation of those atoms, and it looks something like this. So you apply a force, and then you have a displacement in the atoms. So initially, those atoms are some sort of equilibrium. It takes a lot of time, a lot of effort to separate them. But then eventually, when you reach a critical point, then separate them becomes much easier. And at some point, the atomic bond strength is broken, the bond strength is broken, and therefore those atoms are free to go apart. That's the idea. And of course, if you have this force versus atom displacement, the area under the curve will give you the energy. So there's an energy associated with separating atoms. That's the idea, basically. I said, well, if we take that approach and extend it to the general case of a material with many atoms and a given crack length, he said we can consider that we have many atoms that we need to pull apart. So the energy required to pull apart those atoms will be basically this, what you see here, and this will be the area required to create a new surface. And because we have 2 new surfaces, we break every time a crack grows, we have surface on the top and another on the bottom. That is 2 times sigma s, so gamma s, or gamma s is the energy required to break atomic bonds per unit surface created by the crack. Then you have a crack length A, and then you have a thickness, of course, because we should think in 3D. This 2D picture that we're seeing has a thickness of B, so that is the area. So you're breaking a lot of atoms. The energy that you need to break to create a surface is gamma s. Because we have two surfaces is 2, and then because we have a crack of length and a plane over b, so we multiply by AB. That's the idea. So that is consistent with thermodynamics. The energy has to go somewhere, and there seems to be an energy required to separate atoms apart. So the idea was, in order to make a fracture process consistent with thermodynamics, again, the energy cannot just disappear. Energy must be transferred from one place to the other. So he thought, for the fracture to happen, the energy that will be made available, for the point at which failure will happen will be when this energy that is stored in the material, that is released from the growth of a crack, is greater or equal to this energy here. So you need this energy to create a crack. This energy must come from somewhere. So the energy that you're storing in your material, the energy that is going to be released when the crack grows, has to be equal or larger than this bond strength. That's the only way we can describe fracture mechanics in the context of thermodynamics. So in other words, what this means is that a crack will grow if the energy stored in the material is sufficient to overcome the energy required to create two new surfaces. That's the idea. So this is what you see here. So you stretch the bonds, you create two new surfaces, and that's the energy. So there's some energy that is stored in the material, and that energy is going to become this. When it's big enough, you're going to release that energy as part of this energy that you need to pull apart atoms. And you can see that easily. So I guess the question is, where does this energy come from, right? So I identified that I have some energy, some resistance to fracture. I need some energy to break atoms apart. And what is this energy? If thermodynamics tells me that in order to achieve this energy, the energy has to come from somewhere, where does this energy come from? Well, the energy comes, of course, from the strain energy. So the work that we do where we apply mechanical loads. And if you think of the simplest case of a bar subjected to uniaxial tension, again, let's think of linear elasticity. If you plot stress versus strain, it looks something like this. So you get it's a linear behavior, and of course the strain energy density is the area under the curve. And then you can see that, of course, we can define the strain energy density U, the strain energy as U being equal to psi, which is the strain energy density multiplied by the volume, and then the strain energy density we know that is 1/2. It's a triangle of base. It's basically 1/2 of sigma multiplied by epsilon, the strain, and then of course because we're using Hooke's law, sigma equals Young's modulus multiplied by the strain, so we get something like this or something like this. This is all the same. So again, the assumptions are linear elasticity, Hooke's law, 1D. So sigma equals Young's modulus multiplied by the strain, and we know that the energy under the curve is the strain energy density. So if we want to calculate the energy of a bar, then it's this. And what happens is that when you break the bar into two halves, then that energy disappears, right? So imagine I'm pulling my bar, and then fracture happens, and I end up with two unloaded bars. So you unload. If you think of a uniaxial tension test, you're pulling your bar. The moment the bar breaks into two halves, you lose all the load. You're not carrying anymore. If you plot the force versus displacement curve, it will go up, and then boom, it will go down. So that energy that we have stored, eventually when things cracked, you unload your sample, and this strain energy becomes zero because you have no load anymore. You carry no more stress. So this is the energy, basically. You accumulate enough energy, something happened, that energy went somewhere else, you lost your energy. So this is the idea of fracture. So you are storing energy, this is storing energy, but then when fracture happens, you are releasing that energy. That is the idea. So everything seems to be consistent, right? When we do a uniaxial tension test, we didn't know where the energy is going. Well, it goes into creating those two surfaces. Okay, so then he said, okay, now Griffith thought I have conceptually in my mind what I need to do. Now I'm going to apply this to more mathematically and consider the case of English. So he looked at this semi-infinite plate subjected to uniaxial tension. And I'm not going to do the math, but he basically computed the strain energy. This is the case of a bar, remember, the same, Hooke's law. So, the energy under the bar is 1/2 sigma epsilon. Considering Hooke's law, we get something like this. So this is the bar without a crack. But then he did the analysis, considering that we had a crack of length A. And I'm not going to do the analysis mathematically. You can find in the paper is very nice, the Griffith's paper, 1920, Royal Society. So you can take a look at it there if you're interested in the derivation. But the idea is that whenever you have a plate with a crack, you're going to have two portions of material that are unloaded. And these two triangles, basically, these areas of unloaded material, because of the presence of the crack, are going to be triangles of basically base A and height pi A. So basically what you end up is that your energy is this minus the unloaded material, which is the same, but over this volume, basically, over b pi a to the power of a. So this is the triangle, and then over the thickness, of course. So this is what the stress, these red lines are what the stress field looks like. So you basically, whenever you have a crack, and if of course if this crack occupies the whole thing, then this should go to 0. So this is for the cases of semi-infinite plate, but this allows us to understand the competition between energies, right? Because the total energy in the system is going to be the sum of the energy required to break the atomic bonds and the mechanical strain energy. So this is the whole thing. So remember, this is the energy required to break the atomic bonds. So for a crack to grow, I need enough energy to separate those atoms apart. This is what we discussed before, 2 times the surface energy plus length of the crack by b. And this is what we just derived before here, right? So the energy, the strain energy, minus the unloaded version of my strain energy due to the growth of the crack. And if I plot these things, you see here y-axis energy, x-axis crack length. You see that if I plot, let's look first at the atomic bond energy. So if we look at this guy here, this is the blue line. As you can see, as my crack grows, my atomic bond energy grows as well, because I need to, I need more energy to break cracks over a longer distance. And then if I plot this guy here, you see that initially when a is equal to 0, this is, it has its biggest value. But as a increases, this term starts becoming more significant. So I keep going down, 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 and eventually, it will be 0 when the whole thing is, when the crack has to span the whole thickness. So basically, it looks something like this. So the strain energy as the crack is growing, because I have more unloaded part of material, I'm going down. And if I sum the two of them, I get the red curve here. And you can see that we're growing, growing, but eventually we reach a point. So we basically, when my crack is very small, I need to keep putting energy. I need to keep increasing the load in my sample in order for my crack to grow. This curve is going up. I can only grow my sample if I keep putting energy into it. So I need to keep increasing my applied load. Remember, the mechanical strain, my energy increases with my applied load. But then eventually I get a point where I don't need to apply any more load. Cracking is going to appear in an unstable way. My crack is going to grow immediately without the need for any more applied energy. So there's a critical point where cracking is unstable. The crack can grow without any additional energy input. So, this is a maximums. If we want to get maximums or minimums, as you know, we take derivatives, we equate to 0. And so if you take this, you equate to 0, and you solve for the stress field. This is applied stress. What you get is that the failure of that plate that English thought was just, reaching a critical stress at near the defect, what we figure out is that actually for this plate to fail, the failure stress, the stress on which it will fail, it will not be tiny, because it will require some energy. So it will be this expression here, the square root of 2 times the surface energy multiplied Young's modulus divided by pi crack length. And you can see that you can group this 2 times surface energy into a value that we call critical energy release rate, also material toughness, or fracture energy. So that's the idea. So English was right. The stresses can be infinite if you assume linear elasticity near a defect. However, it's not enough to get a high stress to propagate a crack. A defect would only grow where a critical energy is attained. So your critical load will depend on some sort of critical energy, a material property that will tell you how tough your material is. And I think, I think at this point I'm going to do a 5-minute break. So 2 past 10 we start again. Any questions so far? Don't be shy. Okay, this was probably just a revision for many of you, but we'll get to more interesting things later. Okay, let's do 5-minute break now.